Hey, welcome once again, ladies and gentlemen, to the Simpkins Physics Corner. It's your host, Mr. Simpkins, kicking you with some AP Physics for some dynamics today. Let's jump right into it. You're going to love this unit because there's only like one equation to use. But today we're going to go over Newton's three laws. So let's kick it off with the axiomata sive leges motus, or the Newton's three laws of motion. The first law you probably know is object of motion stays in motion, object of rest stays in rest, unless acted upon by an outside or unbalanced force. Now, just a quick recommendation, if you guys are looking for some OG physics, check this guy out, Professor Julius Sumr Miller, the original. He is awesome, and here's a little link. If you look up this video right here, Julius Sumr Miller, Physics Inertia Part 1, you will smile a lot because he is a beast. Let's take a look at inertia though. All right, inertia is this idea, or if you are a Bill Nye the Science Guy fan, inertia is a property of matter. All right, so check this guy. He's going to do the old tablecloth trick, except, oh, he pulled the whole table out. Wait, that's not the one I was looking for. Let's go for this one. Here we go. He pulls the tablecloth and the objects or the plates stay behind. Right, these objects have inertia because they have mass. Inertia is a property of matter. Mass is how much matter an object has. So if you have mass, you have inertia. And inertia is this property of objects to continue doing what they're doing. If they're at rest, they want to stay at rest. All right, so here's an example of staying at rest, just like the tablecloth trick. How about objects in motion? Well, of course, they want to stay in motion, right? Because that object is already moving. It has mass, it has inertia. Inertia is the property of matter that it wants to continue doing what it's doing. So whether it's a boulder rolling down a hill, or whether it's the Tesla flying around orbiting the Earth, both of those objects, once you put something in motion, it's going to continue doing that until, well, in the case of the boulder, an outside force like running over the guy slows it down or changes its motion. But there's some other implications to inertia. Like, for example, an object in motion stays at rest, or sorry, an object in rest stays at rest, an object in motion stays in motion in a straight line at a constant speed. It's a little bit of a caveat there, right? And how would that work? Well, like, let's say you're driving your car down the road and you're driving really fast in one direction. So let's say you're let's say you're going really fast in one direction. If you all of a sudden try to change your motion, you're going this way. If you all of a sudden try to change your motion, like make a turn, but you're going too fast, something like this might happen to you. Why is that? Well, it's because the car has a lot of mass, it has a lot of inertia, and it wants to keep moving, but it also wants to keep moving in the direction it's already going. I say in a straight line at a constant speed, right? So it's going to take some force, in this case the grippiness of the road, or the force of friction from the road on the car, in order to change your direction. So it's not only are you at rest or are you moving, but it's also the direction that you happen to be moving in. The fourth consequence of this is things that move in a circle are not in a natural state. It takes an outside force in order to keep things moving in a circle. And so as soon as you're not experiencing a force that keeps your circular motion, check out the guy with the red pants here, is going to fly off of this merry-go-round, and we call that tangent. The word tangent comes from math class, and if you have a curve and you place a line on the edge of that curve, that's called a tangent line. And so you can see the path of this guy's motion, he's on the merry-go-round, but as soon as he gets to this point over here, he starts to fly off, and what does he do? Well, he doesn't fly in some kind of curvy path, he flies straight off. That's called tangent, or tangential velocity. And finally, another consequence of inertia, or the first law, is the old water bucket trick, right? So if we consider this guy swinging a bucket of water around his head, at the bottom, of course, gravity would be one of the forces keeping the water in the bucket. But as the bucket is over here above his head, what is going on here? A lot of people want to say there's centrifugal force, and if you watch Julius Sumr Miller, he will call that a nasty thing, all right, because it is. There is no force acting away. If you think there is, I would challenge you to name that force. You can't, because there's not. All right, but the force that is acting is the bottom of the bucket is pushing on the water down. If you consider our example of the car going around a really fast curve, kind of like this, what does the water want to do? Well, the water doesn't want to fly up. It wants to keep going forwards, or tangent. But now the bucket bottom is over here, pushing it back towards the middle. What's the water want to do then? It wants to go tangent. But the bucket bottom is here, pushing it back towards the middle. And so the water doesn't stay in the bucket because some magical, non-existent centrifugal force, but it's actually a consequence of the inertia. The water's inertia causes it to want to continue in a straight line at a constant speed, but the force on the bottom of the bucket on that water prohibits it from doing so, and it makes it maintain that circular path. Let's get to Newton's second law, which is F equals ma. Let's say I slap a Nerf ball that is kind of small, all right? Well, if I slap the Nerf ball, it's going to go pretty far, right, because it's pretty lightweight. What if I take my hand and apply the same force to a bowling ball? Ouch. It's going to hurt my hand, right? It's not going to go very far at all right? So obviously the bowling ball is going to accelerate less given the same force that a Nerf ball would receive, the Nerf ball would accelerate a lot more. Why? Because it has a smaller mass. This is pretty intuitive if you think about it. Before I continue any further though, let's differentiate two things. Students often confuse these terms mass and weight. They try to use them interchangeably. Now, as I say down here, mass and weight are proportional. In other words, if you have more mass, you would tend to also have more weight, right? If you have a big mass, you're gonna have a large weight, but they are absolutely completely different things, because mass is the amount of matter in an object. It's how many molecules you're made of, whereas weight is a measurement of the force of gravity on you. So let's take a spaceman, for example. If I took a spaceman here on Earth, right, it would have a certain amount of, they would have a certain amount of mass, and they would have a certain weight. If I sent that space person to the moon here, now they would have the same mass. It's not like they lost an arm or their leg fell off on the way there, I hope not. But so they have the same mass, but they would have a different weight. Why? Because the force of gravity of the moon pulling on them is a different force than the force of gravity of the Earth pulling on them. So your weight can change based on your location or your gravitational reference frame, but mass is something that remains constant. It's something that is an inherent property of how much stuff you're made of. And remember, the amount of mass you have determines the amount of inertia that you're going to have. So a nice little memory thing I help my students out with is wait, force of gravity. If you just every time you hear this word weight, don't be thinking about mass. Think wait, force of gravity. All right, and so just anytime you think of the word wait, force of gravity. All right, there it is. So now it's the third time. You're going to remember it forever. Let's look at another example. What if I take the Nerf ball now, and I'm not going to change the kind of ball I'm applying force to, but I'm going to change the amount of force that I'm applying to. Well, of course, if I just give it a little tappy, it's not going to move very far, right? But if I give it a large slap, if I slap the Nerf ball, it's going to move really fast, and it's going to move really far, right? And that is another illustration of this idea of F equals ma. Why? Because here, the mass is the same, but a small f results in a small acceleration. A large f results in a large acceleration. Its velocity is going to change a lot, okay? And so this is actually a very simple equation, but it describes all of our motions really nicely. Now the thing is, Newton's second law isn't really F equals ma. It's really sigma F equals ma. And the sigma here is a Greek symbol that means the sum of. So if you add up a bunch of stuff in math class, that's the summation symbol, or the sigma symbol tells you to add up a bunch of stuff. And in this context, what it means is add up all the what? All the forces. Look, sigma F, add up all the forces acting on the mass. That will help you determine the acceleration that mass experiences. So for balanced forces, if forces are balanced, we call that a state of equilibrium, because all the forces are equal, all right? And the object will either remain in rest, if it's at rest already, or it will remain in its state of motion if you're in equilibrium. However, when an object experiences unbalanced forces, the object will be caused to accelerate. That's what F equals ma means. All right. And so if we look at just some quick examples here, let's take a look at these guys. If we look at the net force is another term that we use for this, sigma F. So sometimes we call it the sum of the forces, sometimes we call it the net force, sometimes we call it sigma F. All those things mean the same thing. But if we look at these arrows, they all look the same size. And if force A were 50 and force B were 200, you notice that the upward and downward forces cancel out, if you will. There's 200 up and 200 down. And the left and right forces cancel out. There's 50 to the left and 50 to the right. And so this would be an example of something that is in equilibrium. It would either stay at rest, or if it's already moving, it would continue the motion that it's undergoing right now. Now, however, if we take a look at this, and we define the net force on this one as 900 newtons up, all right, that means that this force would have to be 1100 newtons. Well, how does that work? All right, if we say the net force is 900 newtons up, then that means if we add up the forces going in this plane, in this vertical plane, they would have to add up to 900. Well, how would that happen? Well, if you had 1100 this way, you would subtract the 200 newtons that's in the downward direction. That would give you a net force of 900 newtons up. How about this one? 60 newtons to the left. Well, it didn't say anything about up and down, so that must imply that the up and down forces are balanced or equal or in equilibrium. So 300 newtons up, 300 newtons down. But if the net force is 60 newtons to the left, and I currently have 80 newtons to the left, I would need 20 newtons to the right in order to make that work. Right? 80 minus 20 would be 60 newtons to the left. And when we say the sum of the forces, if you're careful about assigning the sign, positive or negative, to your forces, you actually can always add them up. All right, let me show you what I mean. In this case, we have 80 newtons to the left, right? So I would say negative 80 newtons, and I would say plus D, that's the one I wanted to find, equals 60 newtons. But I would make that negative 60 newtons. Why? Because it's 60 newtons to the left. And then you can solve this equation. You can say negative 80 plus D equals negative 60. You would add 80 to both sides, and that's what gets you 20 newtons to the right. So if you carefully assign negatives and positives with our traditional directions of up being positive, right being positive, left being negative, down being negative, you can actually use that summation symbol, and it works every time. Then we have the net force of 30 newtons to the right. That implies that these guys are equal, right? So I don't know what the magnitude is, but I can say that they're equal. And that must mean that force G is 50 newtons. Why? Because 50 minus 20 gets you a sum, or a net force, of 30 newtons. Let's jump to the last of Newton's three laws, the third law. There's something really interesting happens, and I used to do this in class. I can't because this lesson's virtual here. But if you take two people, and you can see this is a little bit of an unfair fight, right? But if you take two sides of a tug of war and you say, all right, side, you on the left, I want you to pull harder than everybody else on the right. You can't do it. You might not believe me, but I'll show you next time you guys are in class. If one person pulls to the left with 50 newtons, that rope is going to be pulling on these guys over here, this team, with that same 50 newtons. So there's a 50 newton pull here, there's going to be a 50 newton pull experience on the other side of the rope. It's going to kind of transfer, and actually there's a rule of physics that says that the force of tension along the rope is going to be constant. All right, and so that is a useful thing to keep in mind. But basically what we're getting at is for every force, there's an equal and opposite reaction force. All right, so let's take a look at another example, and this is the kind of the second corollary to the Newton's third law. It's that forces occur in pairs. Now this guy is having a tragic morning sliding down his driveway, because normally when you walk, you expect there to be some friction force pushing off of your foot. See, what actually happens when you walk is your foot pushes on the ground and the ground pushes on you if there's enough friction. Well, here there is no friction, so his feet are trying to push on something, but they're just slipping and sliding all over the place. This is what we call force pairs. All right, and so if you're ever asked about a force pair, you're thinking about the interaction between two objects. Foot pushes on ground, ground pushes on foot, that sort of thing. All right. This is a great one. Okay, you can imagine what would happen here. This little guy is trying to hop off of this boat. He's with his friends. Looks like he's old guy. He's got his two girlfriends with him, and he's riding a boat. And he tries to step off of this boat. But what happens here is he pushes off the boat. Well, what happens when he pushes off the boat? Well, of course, the boat is going to push forwards on him, right? That's what lets him get or launched over there to the dock. The problem is, what's the reaction of the boat of him pushing on it? You see, let's go ahead and we'll snip this, and we'll go ahead back to our slides here. He pushes on the boat pushes on him, which is good because that's what he wants to happen. He wants to go to the dock. The only problem is he doesn't make it to the dock, right? Or at least he loses his balance, but now the boat's on its way back, and when he turns around to find it again, he can't, all right? So that's what we mean when we say a force pair. He pushes on the boat pushes on him. Only problem is now he's over at the dock, and when he turns around, the boat isn't there anymore. Why? Because of Newton's second law. This mass of the boat experienced the force from the guy, and if a mass experiences a force, it's going to accelerate in the direction of that unbalanced force. All right, finally, you look at a little something like this. This is kind of both the third and second law. You see we have equal and opposite forces. You might say, well, the bigger guy exerts more force. No, he actually doesn't, because Newton's third law says you can't. They have equal and opposite forces. So they both experience the same force. You're like, well, Mr. Simpkins, why does the woman travel so much faster? Well, it's because of Newton's second law. She has a smaller mass. This guy looks like it's pretty safe to say he has a bigger mass. And if a bigger mass experiences the same force, you get a small acceleration. If a small mass experiences the same force, you get a larger acceleration. So this picture is really nice because it kind of shows you Newton's second and third law all at once. So the summary for today is Newton's three laws. All right, you've probably heard these in middle school. That's why I wanted to do it pretty quickly and show you some examples. The AP twist to this is going to be applying these ideas to lots of different kinds of scenarios. So you want to be familiar with the terms like inertia and tangential velocity, right? If something's moving in a circle and it flies straight, that extra piece there of objects in motion stay in motion, objects at rest stay at rest, and objects that are in motion tend to go in a straight line at a constant speed the way they're already going. Newton's second law is F equals ma, and now we know the AP version is sigma F equals ma. We're going to get into next week drawing free body diagrams to express all the forces acting on things, because that will help us organize our problem-solving strategies. And then, of course, the third law, for every force, there's an equal and opposite reaction force, and that forces occur in these things called force pairs. These are the three laws for Newton, and these are the three big ideas that we want to keep central in our mind as we start to unpack equations and do vectors and get complicated forces all over the place. Always come back around to these ideas of Newton's three laws. This is Mr. Simpkins in the Simpkins Physics Corner. I'll catch you next week for forces, vectors, and F equals ma in SET.